and welcome to the podcast of Loughborough University's Institute of Advanced Studies, a podcast where our international fellows discuss the most pressing issues of today that we're all facing and share their exciting research ideas. We hope you enjoy today's talk. Thank you for tuning in. Good afternoon, everyone. It is afternoon now. I was a little bit too keen on afternoon early on. And welcome to the International House. I'm Professor Ksenia Chmutina, Director of the IAS. I'm really sorry I couldn't be with you in person today, but more lunch for you because, I'm very good at eating those sandwiches. Well, welcome to the IAS. It's really wonderful to see so many of you in the room today, and there are quite a few of us online. And it just shows how excited people are to hear more from our chemist colleagues. We haven't had a chemistry seminar for a while, so it's wonderful to see all of you today. And of course, welcome to our IS fellow, Robina Begum, who is joining us from Punjab. Welcome, Robina. I hope you're having a nice time at Loughborough at the IAS. And before I let Sandy introduce Robina properly, just a couple of housekeeping rules. So for those of you joining us online, joining me online, joining the seminar, there is a Q&A section. So if you have any questions or comments, please post them online, and Kieran and the team will be monitoring that, so they will be able to ask Robina questions. For those of you in the room, if you have any questions, again, comments, please keep those to the end of the presentation, and then there will be time for Q&A, and of course you can continue over lunch. We are recording the presentation, but we will not be recording questions and answers. So the presentation will be released on our YouTube channel and as a podcast, but not questions and answers. So feel free to ask absolutely anything. With this, I hope you enjoy the seminar today. And Sandy, over to you for the introductions.
Okay, I shall come over here and stand at the front of the room. So it's my great pleasure to introduce Robina Begum to everybody in the room. Robina first came to the UK as a Commonwealth scholar. She worked at the University of Liverpool and she got her PhD in 2019. She currently is an assistant professor at the School of Chemistry in the University of the Punjab in Lahore in Pakistan. She's got ongoing collaborations with different colleagues across the world. So, for example, Professor Chu at the University in New York, Dr. Goran in the Department of Chemical Engineering here, and Professor Wu, who is from the University of Xiamen in China. She has published 106 peer-reviewed papers and currently is about 5,500 citations of those and has an H index of 45. She has served as the guest editor of Advances in Microgels, and she has a high contribution in her field. So she has classed as 2% of the most highly cited scholars by Elsevier for the last 4 years. Various international level funding from across the world, and I'm very pleased to say that she's joined us in the department as an IAS scholar, and we will be working together over the next few years to put together some more applications to bring Robina to and from the university. So without further ado, I'm going to hand over to you to talk about your background in microgels and what they can do for us. Okay.
Thank you so much. First of all, I would like to pay my sincere gratitude to Dr. Sandy for the kind introduction and for inviting me at the academic forum of Institute of Advanced Studies, and for giving me the opportunity to present my work in front of you. And it is a great matter of honor and pleasure for me to be here and to do some international collaboration with the Department of Chemistry, Lahore University. And I'm very much thankful to Institute of Advanced Studies for making this possible, and for making this possible in terms of people from across the globe come interact with each other and do collective work to solve the different type of global challenges as well. So before going deep into my research area, as you can see from the topic as well, that I'm working in the area of organic and inorganic hybrid microgel, mainly for the purpose of catalysis. I would like to just go through some brief terminologies which I am going to use during my presentation. That, as I told, that I'm working on microgel for catalytic applications. So gels are basically cross-linked polymeric network, and we can classify them on the basis of their size into nanogels, into microgels, and into macrogels. So if they have their size in the range of nano range, like from up till 100 nanometer, we can classify them as nanogels. And if they are in the range of like 100 micrometer normally, generally, and we classify them as microgels. And if their size is bigger than this, then we classify them as the macrogels. And if the so this microgel network contain a liquid within their network. If that liquid is water, then this type of macrogel is known as hydrogel, and it is a bulk gel. So my research area is focused on microgels because no, why not nanogels? Because after the presentation, you will realize that we have to separate them through centrifugation. So we have to reuse them. So for nanogels, it is difficult to regenerate them because of the smaller size. And for the bulk gel, the properties, the diffusional properties, which is associated with my work, is difficult with the bulk gel, that is the macrogels. So I'm working on the microgels, and these microgels are classified on different bases, like they are classified on the basis of their morphology, that how they look, how they shape, and on the basis of their cross-linking ability and their basis of their responsive behavior. So on the basis of morphology, we classify them into homogeneous and heterogeneous microgels. So homogeneous microgel is such type of microgels, their network is seen throughout the microgel. The same material is there, that they are homogeneous, uniform throughout. While for heterogeneous material, there are two different materials. There is a core inside the microgel, which can be of any material. It can be any metal atom, or it can be some silica, or it can be some polystyrene, etc. And after the core, there is a network around the core, which make a network. So this type of microgel is known as heterogeneous, and one example is the core shell microgel. So I am working on both, and most of my work, research work, is based on homogeneous microgel, and the proposal which we have submitted to the IAS and for future work, that is on core shell microgels. On the basis of the cross-linking ability, these microgels are physically cross-linked. Physically cross-linked microgels are those which have temporary interactions. So we can't use them under harsh conditions. So they are not as much useful for us. So we used chemically cross-linked microgels. So they can work under harsh conditions as well, and they are comparatively stable. So that's why we are working on chemically cross-linked microgels. On the basis of responsive behavior, this is one of the very important property of these microgels, that they show response towards an external stimuli. And what type of response they show? They just change their size. They decrease or increase their size. How? If an external stimuli is introduced into the system, like for example, temperature, or we can change pH or just ionic strength, then they show responsive behavior. So on the basis of their response to external stimuli, we classify them onto responsive and non-responsive microgel. So I'm working on basically on responsive microgels. So one of the typical example of the responsive microgel is the thermoresponsive microgels. So as the terminology states, that thermoresponsive microgels means that these microgels responds towards the change in temperature. So when we change the temperature, they change their sizes. Like we can see from the graph as well, and from the figure, that by decreasing the temperature, they got swollen, and by decreasing the temperature, their size becomes shrunken. So this property is very helpful in our different applications. So why these microgels shows responsive behavior, it just the property of some monomers. Like currently here I am showing anisopropyl acrylamide, which shows which make it responsive. So these microgels are responsive because of some monomers which show hydrophilic or hydrophobic nature by changing the temperature, which change their size. We can see from this graph that by changing the temperature, or by increasing the temperature, there's a gradual decrease in the size of the hydrodynamic diameter of the microgel. And at a point like around 30, 32 degree, there is an abrupt change of in the size of the microgel, which is because of the a specific monomer which is present within the network of the microgel. The abrupt change which take place in the hydrodynamic diameter at that specific temperature is known as volume phase transition temperature. And this volume phase transition temperature is specific for every monomer. Like for one monomer, it is like for this monomer, it is like around 32, 35 degree. And for some other monomer like methacrylamide, it is around 40 something. So that volume phase transition temperature at which there is an abrupt change in the structure diameter, it depends upon the type of monomer which we use. And further, this responsive microgel size is characterized by using the TEM, and we just found that they have uniform size distribution, and they are spherical in shape, and we just check the size and their uniformity from this analysis. So this is one example of the responsive microgel, how they respond towards external stimuli. So because of this responsive behavior, these responsive microgels can be used for pH sensing, for temperature sensing, for glucose sensing, and drug delivery and absorption of toxic and heavy metal ions from different bodies, nanotechnological application, and tunable catalysis. So these are different areas in which different people are working by using these responsive microgels. So our main focus is on their nanotechnological application and tunable catalytic applications. So going towards the nanotechnological applications, in what is the role of these responsive microgels? These microgels serve as a microreactor for the synthesis of the nanoparticles and as a stabilizer for the stabilization of the nanoparticle. So we use these responsive microgel as a microreactor for synthesizing different type of metal nanoparticles, and after that we are stabilizing these nanoparticles within the network of this microgel. And another application is that the tunable catalysis, like we use these responsive microgel after incorporation of the nanoparticles within the network, we are using them as a catalysis. So one example in which these microgels are used as a microreactor and stabilizer for these nanoparticle is this shown in the slide. Here I have introduced a new terminology that is also mentioned in my introduction slide, that was hybrid microgel. So when we introduce metal nanoparticles within the network of this microgel, so the network of the microgel is comprised of an organic material, like the monomer which we used is of organic nature, like it can be acrylic acid, polystyrene, napalm, etc. And the metals nanoparticles which we have loaded into the network of this responsive microgel is of inorganic nature. So that's why we are now calling them as a hybrid microgel, because it is a combination of organic and inorganic materials. So how we synthesize these hybrid microgels is that there are different methods for synthesis of these hybrid microgels. The one which I'm showing here is, first of all, you just use different monomers under some specific conditions under nitrogen purging, and use some initiator and cross-linker, and synthesize a specific microgel by using free radical precipitation polymerization method. And then after the synthesis of the microgel, as I told, these are responsive microgel. We can just change their size by changing some stimuli. It depends which monomer is present within the network. Is it pH sensitive, or it is temperature sensitive, or it is ionic strength? It depends upon the type of the monomer we used. So if it's pH sensitive, we just change the pH to in order to swallow the microgel, and then we introduce the metal salts to get into the network of the microgel, and then these metal salts are get reduced by some reducing agent, and as a result we got hybrid material which contains inorganic metal nanoparticles and microgels. So this we have prepared several different types of homogeneous hybrid microgel systems containing different types of monomers and having different types of metals. So this is the one way to prepare this hybrid microgel. There are two more ways to prepare these hybrid microgels, but this is the more effective way. The other two ways are the one in which we have to prepare separately metal nanoparticles and microgel, and then we have to combine. The third way is that you first prepare nanoparticles, then build a cross-linking network of microgel around them. So we thought the most effective way in which they are more effectively stabilized within the nanoparticle within the network of the microgel is the hybrid microgel, in which firstly you synthesize the microgel and then introduce the metal ions and reduce them by some reducing agent and get your hybrid microgels. So, on the basis of the morphology of these hybrid microgel, we can classify them into different types. So, the one which I talked earlier as well is the homogeneous microgel, which is uniformly loaded with the network nanoparticles within the network. This is the one. The second one is the in which there is, as I characterize on the basis of their morphology, that there are core shell and homogeneous. The second one is of the core shell, in which core is made up of a specific material. It can be like here, it is of some metal atom, and then a network is built around it, and it also got some nanoparticles within it. Then the third type is in which the nanoparticles only cover the surface of the microgel network. They are just on the surface of the microgels. They didn't go deeper into the microgel core. And the fourth one is the core shell microgel, in which core is made up of some material other than metal, like it can be alumina or it can be styrene, etc. The last one is the hollow hybrid microgel. Everyone has its own application, pros and cons. So the other one, the last one is hollow hybrid microgel, in which the central space is hollow, and around the hollow space there is a network which contains different metal nanoparticles. So on the morphology, we classify these hybrid microgels into these different types. So my work is basically on the homogeneous microgels loaded with the nanoparticle, the first one, and the heterogeneous one, in which core is made up of some different material, and then around the core we build a network, and then we introduce some nanoparticles into the network. So this is one of the typical test example which I brought to you people for the homogeneous, in which the first one, homogeneous microgel, in which we synthesize a microgel using three different monomers. The one is the chitosan, anisopropyl and acrylic acid. We use the three different monomers. APS, ammonium persulfate, is used as an initiator, and SDS, sodium rhodesyl sulfate, is used as a surfactant. And we did this experiment under nitrogen purging, and free radical precipitation polymerization method was used in order to synthesize this pure microgel. After the formation of the pure microgel, then this was loaded with the silver ions, and for this purpose silver nitrate solution was used, and then these metal ions were get reduced by sodium borohydrates, and we got our required nanoparticles. After then this is the example of homogeneous hybrid microgel, and after getting our required hybrid microgel, we characterize again by using TEM analysis, so that we can know the shapes and the size of the hybrid microgel itself, and along loaded with the nanoparticle as well. So one of the property associated with this metal nanoparticles is their absorbance in UV visible region. So they have the property which is surface plasmon resonance spectroscopy. They're associated with them. They can absorb in a specific region in UV visible. So for silver, as we can see from the graph, that if we just do the UV visible spectra of simple microgel, we didn't get any absorbance. But when we did it for the hybrid microgel, we got a good sharp peak with a lambda max, around 400 something. So these silver nanoparticle absorb in this region, so we can characterize them by the UV visible spectroscopy as well. So then we tested the stability of these nanoparticles within the network of the microgel system. So their lambda SPR is a function of their time, size, and it depends upon their size and shape and the distance between the nanoparticles. And from the stability graph, we see that there's no shift in the noticeable shift in the peak of the lambda max for the silver nanoparticle, which shows that even they are stable after 60 days or well. So it can tell us that these nanoparticles are, we can stabilize these nanoparticles within the core of the microgel for a longer time, and we can use them for different applications. So this is the one example of the homogeneous microgel. The other example which we used on many different type of substrate to check their catalytic ability. So this is the one in which we used N-isopropyl acrylamide and acrylamide as an isomer, and we synthesized NIPAM and acrylamide based microgel, and usually it comes in the form of white milky dispersion, and then they were loaded with the metal ions, that is silver in this case, and that we reduced them and we got our required and desired nanoparticles. Then this hybrid microgel was tested for one of the model reaction, which mostly is used in literature as well. That is the reduction of 4-nitrophenol. So 4-nitrophenol is a toxic chemical, mainly in our country. Usually it's found in effluents coming from the industry. And the bad thing about this is that it is soluble in water. So it is very difficult to remove it from the water bodies. So we convert them into 4-aminophenol, which is a useful chemical and can be used as an intermediate in different other reactions as well. The other reason to choose usually this nitroarenes as a model reaction to check the catalytic activity of this system is that they absorb in UV visible region. So we can check the progress of the reaction with the passage of time. So as we can see from the graph of the UV visible spectroscopy, that with the passage, this is the graph which shows the reaction progress. That, as I mentioned, that 4-nitroarenes has the ability to absorb in the UV visible region. So we can see that with the passage of time, the absorbance because of the 4-nitrophenol getting uh, minimized, and the 4-aminophenol is comparatively getting increased. And at a certain point, there is no absorbance because of the 4-nitrophenol in this graph. So that's the modern reaction which is tested, in which this hybrid system is tested as a catalyst, and it gives very good results. And after monitoring the reaction with UV visible spectroscopy, we we separate and purify our product, and we characterize by spectroscopic technique like proton NMR, C13, and mass for our product. And we got these kind of spectra for our substrate. After getting the successful result from our model reaction, then we tried different type of substrates for this, and we tried almost 20 to 24 substrate of nitroarenes having different type of functionalities at different positions, and we get good to excellent results for this. And most of them have percentage greater than 70%, and these are all the substrate which we tried and got reduced by using this hybrid system. And there is we believe that there is a little bit variation in time and percentage yield of the product, which is only because of the different groups, electron donating or withdrawing groups present in the structure of the nitroarene at different position, which may be responsible for their reaction time or their percentage yield. So these were the substrates which we reduced by using this catalytic systems, and we got good results for all of these. After this, we tried the same system with another metal just to check its ability. Either it can stabilize some other metal, or it can do the same job or not. So for this purpose, we use the same microgel, but we just change the metal salts within the network, and in order to get some different kind of nanoparticles. And for this purpose, we use palladium salts, and we got palladium nanoparticles. And again, first of all, we tried with the test reaction with the one reactant, and we got very good results for this as well. And again we characterize, purify, and after separation of our product by spectroscopic methods. And then for the same system, with the palladium nanoparticle, we again tried different type of substrates containing different types of functionalities, and again we got very good results. For all of these substrates were successfully reduced by using the same system but with different nanoparticle. So it tells us that our system is helpful with not only silver, but we can use other metals as well within the network, and they are equally good for the catalytic activity, and their stability at the same time is better with this system. So this is the substrate scope which we tried for the palladium nanoparticles. And now this is the we tried some coupling reactions as well with this palladium nanoparticles within the network of this microgel, and we also got very good results for these substrates. And this is the proposed mechanism for the reduction of the nitroarenes on the surface of our nanoparticles, which are, so and we assume there is the diffusion of reactant in from the bulk region to the surface of the nanoparticle, which are present on the surface and within the network of the microgel, adsorption of our reactant molecules on the surface of the nanoparticle, and they got interaction between the nitroarene part and the sodium borohydride part. And after interaction, the hydride ion shift take place, and it get reduced, and then desorption of the product from bulk region of the network into the out of the network into the atmosphere because of diffusional barrier. So this is the proposed mechanism for this reduction of nitroarenes. So these microgels, homogeneous microgels up till now, which I talked about, are very good in responsive behavior towards their external stimuli. They have long-term stability. We can recycle them, and they have high catalytic potential. But the problems which we are facing, which are associated with these homogeneous microgels, are those we need very high speed centrifugation in order to recover them. So which is a challenge as well, and diffusional barrier faced by the reactant. So it is difficult for the reactant to go inside the network to approach those nanoparticles and get reduced on the surface. And the other is that if we you have to use relatively high content of metals, because some atoms have to go into the network as well, and which are not easily approachable by the reactants afterwards. So, and as I mentioned, that nanoparticles within the core are not easily accessible as well. So, in order to address these challenges which are associated with the homogeneous system, we submitted the proposal under IAS with Dr. Sandy that why not to prepare some core shell microgels as well and do some different type of stuff with it. And we proposed that why not to prepare a core with the styrene and then build a network around it of NIPMAM, and then we have to incorporate some metal salt into the network, and then we will reduce it and we will got the nanoparticle. So they are easily as comparatively of easy to separate after centrifugation. We can recover them easily and we can reuse them, and we then further use in different fields like for absorption of heavy metal ions or and catalysis by introducing different type of nanoparticles. So this was the proposal, and we did some experimental work that we synthesized the polystyrene core, and then as we can see, it is a milky white dispersion. And after the formation of the polystyrene core, we synthesize the shell around of NIPMAM around the microgel, and by using the same free radical precipitation polymerization method. And then this was used to test the catalytic applications of this hybrid system, heterogeneous hybrid system, and we got good results for the catalytic activity. The catalytic activity was again checked and progressed by the UV visible spectroscopy, and we characterize our hybrid and microgel by using time analysis as well. So this was the unpublished work, and we are still working on it. And for the work in progress, we submitted our one of the review article with Dr. Sandy. Already the revision is submitted, and for the current work, we are doing some work on it, and soon we will do that experimental work will be come in the form of a manuscript. Dr. Shukanzu from City University of New York also is involved in the work with us, and she is also collaborating with us and helping us in some characterization as well. And at the same time, we are preparing some more joint proposal and for our future collaboration. Currently, we will prepare our application for researcher collaboration grant under RSC. And I hope this platform will help us to transfer students, especially from Punjab University, under Commonwealth Split Side Scholarship. And we will try to send students under ASIP, which is a program of Higher Education Commission Pakistan as well, and some other short-term and long-term. We will search funding so that we can exchange our student and they can learn more from the lab of Dr. Sandy. So I'm very much grateful to the Institute of Advanced Studies that they gave me the opportunity to come here and learn so many things and collaborate with the help of this. I'm able to collaborate with Dr. Sandy and learn so many things from her. And I'm very much grateful to Dr. Sandy for her generous hospitality, for her guidance, for her care, especially throughout my visit up till now. She is very caring and she take care of everything, and she is available all the time on even my single email. She just reply, and she is trying to solve my each and everything for me, and she is such a nice lady, and I'm very much helpful thankful to Dr. Sandy, and in future I'm very much hopeful I will collaborate further now with her, and I will try to take Dr. Sandy to Pakistan as well, so that she visit our labs as well, and we will come back again on some other project. And I hope that this linkage, which is developed because of funding from IAS, we will take it to long-term collaboration, and we will get many good results from this collaboration. And thank you so much for all my students, especially of our master's and PhD students who are behind all these experimental work. Thank you so much, everybody, for listening me. I hope you people are not very much bored, because I was talking to Dr. Sandy that I tried to minimize the presentation because area is different for different people. So it is very hard to listen to a long presentation. So I hope you will understand. Thank you so much, everyone.
Thank you.
Thank you for listening to the podcast of Loughborough University's Institute of Advanced Studies. A quick reminder about how to stay connected. You can find us on Blue Sky, LinkedIn, and Instagram, and you can also watch the presentations on YouTube. The podcast is available on all the major platforms. Please download, share, and most importantly, subscribe. See you next time.